technology. But today I'm going to be talking to you about some work that I did for my honours thesis at the Australian National University, supervised by Dr. Patrick McGlynn and Professor Cedric Simonal. So in a single sentence, this talk focuses on quantum field theoretic approaches to quantum tunneling through external potentials. But I think given the topic of this seminar series, it's useful to first say what this talk is not. So this talk does not address problems associated with false vacuum decay or the tunneling of field configurations. So rather what we're looking at is we address tunneling of particles through localized potentials. So by localized, we mean potentials which aren't Lorentz invariant. So something like, a rectangular barrier or a Coulomb potential, where we keep our theory simple enough such that we can still capture tunneling effects. So for this purpose, we neglect spin and just consider a neutral scalar field theory. So just briefly, this talk primarily covers our two recent papers, which have been accepted in EPJC, and it's broken up into approximately 2 sections, which cover both of these papers more or less separately. So the first is tunneling amplitudes through localized external potentials from Feynman diagram summation. And this is where we build a formalism of tunneling using QFT, but still restrict ourselves to relativistic quantum mechanics. And then in part 2, we extend the results of part 1 to include quantum corrections to tunneling amplitudes of neutral scalar fields. So I'll explain this separation in more depth later on. Okay, so a good place to start is how ubiquitous quantum tunneling actually is. So, its physics unsurprisingly underpins things like tunnel diodes. We know that proton tunneling causes DNA mutations. It's relevant for scanning tunneling microscopy. But I think one of the more interesting applications is the fact that quantum tunneling drives stellar nucleosynthesis. So particularly when we have light nuclei fusing, these fusion reactions play a really important part in the late stages of heavy star nucleosynthesis, should I say. And particularly at these energies, the primary mechanism in which this occurs is via quantum tunneling. And interestingly, these deep subbarrier fusion reactions are not theoretically understood. So we don't have microscopic models which can predict these fusion cross-sections and therefore their tunneling probabilities. And they have quite complicated, resonance structures which are crucial to describe well in order to predict key aspects of nucleosynthesis. So this particular problem highlights the fact that tunneling is still not well understood. So this is really a twofold problem. So the first is what I was alluding to before, which is that we don't have a complete theory of interacting many particle tunneling. So we don't know how a strongly interacting composite object collectively tunnels. So something like a nucleus, which is a collection of strongly interacting protons and neutrons. So typically in nuclear physics, we sometimes approximate dynamics using semi-classical mean field methods. But the issue with these in the context of tunneling is that the semi-classical nature actually suppresses tunneling behavior. So this means that applying these methods to, let's say, subbarrier fusion cross-sections, you'll find that you can't reproduce tunneling. So there has been some work extending this via Wick rotations, so by essentially imaginary time mean field methods. And these have shown some promise for small systems. So you find that you can recover tunneling behavior, but that these are numerically unstable for more realistic systems. So with this in mind, we also have a slightly more fundamental problem associated with tunneling, and that's that quantum mechanics conserves particle number and particle type. So this more fundamental problem prompts us to sort of take a closer look at the foundations of tunneling, and in particular how we describe interactions. So we know that in the real world, any interaction implies the destruction and creation of particles. And the way to properly treat this is with quantum field theory, where we don't have particle number conservation. So the reason why this is an issue particularly in quantum mechanics, is that we're unable to describe things like pair production processes, which are induced by strong potentials. And as we'll see, this actually results in paradoxes for single particle tunneling in relativistic quantum mechanics. So one such paradox is the Klein paradox. And this gives us some motivation for why we might want to apply QFT to the problem of tunneling. So the Klein paradox arises when we have an incoming fermion scattering off something called the Klein step. And the Klein step is essentially a large step potential such that it's greater than twice the mass of the electron. And we find that when you solve this using the Dirac equation and just boundary condition analysis, you get a reflection coefficient greater than 1 and a transmission coefficient greater than 0. So on the surface level, this appears to violate unitarity, and therefore we have a paradox in relativistic quantum mechanics. But the way that this is resolved is by invoking electron-positron production at the barrier. And fundamentally, in order to do this, you have to go beyond a single particle description of relativistic quantum mechanics. Like QFT is necessary to solve this paradox. So while this particular example is not strictly a tunneling problem, it does give motivation for why we should perhaps treat interactions in scattering problems and tunneling problems more carefully. And this really brings us to the focus of this work. So we focus on the foundations of interactions and single particle tunneling by using the framework of quantum field theory using primarily analytic methods. So we do this for simple spinless systems. So we really want to consider a quantum field theory which can describe tunneling without having additional complexity induced by spin or charge. And we're interested in the question of how do QFT effects affect tunneling probabilities. Just to be clear, we don't anticipate to fully solve an interacting quantum field theory for a many-body bound state system. Like, this is simply beyond the scope of the work. So really what we're trying to do is just ask the question, how can we treat a single particle tunneling in an interacting QFT? And yes, we don't anticipate this to be able to extend it to a realistic model at this point, though that is a future goal. So this brings us to the two parts of this talk. So the first is we want to develop a formalism for how we can describe tunneling in QFT. So in this part, we just consider relativistic quantum mechanics, but we use QFT methods to derive known results. And this is like a fundamentally single particle theory in this section. And then once we have this formalism, we build upon it to ask the question, how do things like loop diagrams and QFT corrections impact tunneling probabilities? And how can we actually include these in a useful way? So this is the many particle theory. Okay, so let's review the system that we're considering. So we're considering single particle states, neutral scalar fields, which interact with some external potential. And these states are described by asymptotically free incoming and outgoing states characterized by some momenta. So just to emphasize, they interact with the external field in the Klein-Gordon-Lagrangian via this particular term. And like I said, this external field is localized and could be something like a Gaussian potential or a square barrier. And typically what we're interested in is the scattering matrix elements associated with this problem. But in general, this element has some functional dependence on the potential, but there are actually no general solutions for arbitrary potentials, and we should expect this because we haven't solved the Klein-Gordon equation for arbitrary potentials. So typically, the way that we would approach a calculation like this in QFT is we would calculate a Taylor expansion about the free solution and then treat this interaction as a perturbation in the coupling to the potential. So essentially treat the potential as a perturbation. But this presents issues in the context of quantum tunneling, and I will explain that now. So here what I'm showing the transmission reflection for a rectangular barrier as a function of dimensionless momentum. And we can see that, so what I've done is I've plotted the perturbation series to different orders in this coupling constant. And we can see very clearly that the perturbation series breaks down exactly at the barrier. So while it can describe above barrier scattering, it's unable to describe tunneling, which is obviously the regime that we care about. So this highlights sort of the key, what makes this problem quite difficult. And that's that QFT relies on perturbative calculations, but tunneling is a non-perturbative phenomenon. So, any approach needs to reconcile these two facts. Okay, so let's just recap the system we're talking about. Again, we have a neutral scalar field coupled to an external potential via the Klein-Gordon-Lagrangian. And I want to emphasize this is still just relativistic quantum mechanics, so we don't have self-interactions present in this system. So still essentially a free field, except for the interaction with the external potential. And we can think about what the scattering matrix element looks like diagrammatically, and it'll be a sum of these particular Feynman diagrams to infinite order. And just to be clear, this symbol here indicates a coupling to the external field. So for our one particle incoming and outgoing states, these are all the Feynman diagrams which will be generated. So as I said before, it's a single particle theory, so we don't see loops or self-interactions. But because we want to describe tunneling non-perturbatively, we need to sum an infinite number of Feynman diagrams, or sum this series non-perturbatively. So one way to do that is we can consider, how do we actually describe the nth order term in such an expansion? And we can notice that, for instance, if we can just consider the third order term, it can be factorized into a second order term multiplied by some vertex function and then integrated with some appropriate measure. And this allows us to define a recursive equation for the nth order term in terms of the n-1th order term, where this is just the free scalar propagator. So in principle, we can solve for the nth order term if we know the previous. And then we can invert this equation such that the solution for the infinite sum corresponds to an integral equation, which again has no general solutions as we would expect. So recalling that actually the goal of this work is to demonstrate a proof of concept that we can use QFT and Lagrangian methods to recover tunneling. This particular equation prompts the question, can we find a potential which would make solving that integral equation particularly easy? And it turns out we can. So one such potential is a delta function potential in position space. And we find that this generates a geometric series of S matrix elements, as we'll show. So some might argue that a delta function is somewhat pathological, but delta function is the limit of a rectangular barrier as you keep the area the same and take the height to infinity, and therefore can be a reasonable approximation for very deep sub-barrier tunneling problems. And we can also use delta functions to approximate other functions, much in the same way that we discretize functions with like rectangular slices. Okay, so we find that when we compute the S matrix elements and then sum them, we have an expression for the total S matrix element, which looks like this. So just to emphasize, the way we've actually summed this is via analytic continuation. So we have to sum this Feynman diagram series in the perturbative regime, but then analytically continue to the tunneling regime. Now, a natural question is, how do we actually go from these S matrix elements to tunneling probabilities? And it's fairly straightforward. So we integrate with appropriate measure over the negative momentum. This is for the reflection coefficient, and then over the positive momentum for the transmission coefficient. This is assuming we have a particle incoming with some positive momentum. And we find that once we actually perform these integrals, we obtain reflection and transmission coefficients of this form, which agree exactly with the relativistic quantum mechanics result that you would get with the Klein-Gordon equation, just doing boundary condition analysis and matching. And this is quite important because it's verifying that we can, in fact, use these QFT methods to recover known results in relativistic quantum mechanics, and demonstrates that, this formalism at least has some promise. We've also shown that we can reproduce these results for a double delta potential. These are slightly more interesting because we have a natural length scale which means that we can recover things like oscillations in the tunneling probability, which are of course fundamentally quantum effects. Okay, so that essentially concludes part 1 of the talk. And that brings us to the second part, which is perhaps the more interesting question of how do QFT corrections impact tunneling? So we've shown how we can describe tunneling using QFT methods, but now we want to introduce additional physics. And one way to do this is to simply add an extra term in our Lagrangian. So we ask how does the presence of some new quantized field affect the tunneling of the original field? And to do this, we add the simplest interaction we can, which is a cubic interaction with another quantized massive neutral scalar field. And our interaction looks like this. So effectively, in terms of diagrams, it just has the effect of adding an extra vertex. And I also want to reiterate that we still have the interaction with the external field as before, but our new field doesn't interact with that particular term. So we still have the same vertex. So what we want is we want to consider the S matrix element, and we want to look at but now it's more complicated because we have to account for all the possible interactions in this, interacting quantum field theory. So it turns out it's slightly easier to work with a different mathematical kind of object called the 2-point correlation function, or the Green's function. So for the rest of this talk, we will deal with this particular quantity. That's also called the dress propagator. But the relationship between this and the S matrix element is fairly straightforward, and I'll just elaborate now. The 2-point correlation function can be related to the S matrix element via the LSZ reduction formula. So you find that when you have poles in the 2-point correlation function, this is when we see particles in the S matrix element. Now, the reason why I highlight this is a slightly technical point and not something we really discuss more is just to say that essentially solving for this dress propagator will give us all the information we need. We can easily go between this and the S matrix element, and therefore do reflection and transmission probabilities. Okay, so let's consider the dress matrix. The dress propagator to perturbative order in U and E. So we see that even at this low order, we generate diagrams which have loops. So this is indicating that we have these quantum corrections already, and we still have our initial vertex term. So you can imagine that as we go to higher and higher orders, as anyone who's familiar with QFT knows, we generate factorially more diagrams, and they become more and more complicated. So it's really not feasible to sum these diagrams perturbatively. And it prompts the question, which of these terms are actually most relevant to tunneling? So for instance, we can have a look at diagrams like this, and these are self-energy diagrams, and we see that they're actually momentum conserving. So they don't interact with the external potential. So it's natural to think that these won't actually have an impact on tunneling because we don't have any exchange of momentum with the external field. So, we don't want to include diagrams like this in such a dress propagator when we're just looking at the effects on tunneling amplitudes. However, looking at diagrams like this, we can see that these are the sorts of terms that we want to retain. So we have to find a way to systematically generate diagrams which we want to retain, so diagrams which are relevant to tunneling. And one way we can think about this is we can imagine we have a term we already have, and then subsequently generate higher order terms by sort of compounding these diagrams like this. And we can do this with loop terms as well. And then this is just sort of a like an intuitive way to think about this process. But effectively what this allows us to do is it allows us to generate a self-consistent equation for the dress propagator, which includes tunneling corrections, and which encodes interactions with both fields to all orders. So when I say self-consistent, I mean that, I can see I've highlighted in this pink box here that this dress propagator actually appears with some complicated dependence on both sides of the equation. And this This partial diagrammatic sum is effectively a Hartree-Fock type approximation because we're only restricting our summation to a restricted class of Feynman diagrams. And just to emphasize, this does in fact go beyond relativistic quantum mechanics, and these are the terms with the loop corrections which would encode these QFT corrections to tunneling. So this is really where the interesting physics is. So let's just unpack what this equation means in a little bit more detail. So we can imagine that if we were to try and solve this iteratively, at 0th order, or for the first iteration, we could approximate the dress propagator just with the vertex function. And if we were to then insert it back in, we would generate a new set of diagrams. And if we were to continue doing this, we would generate more and more diagrams at every order. So doing this ad infinitum would get us, would result in the complete set of, well, complete class of Feynman diagrams that we're interested in. And in particular, at every order, we only generate at every iteration, we only generate unique diagrams. So I do this just to sort of give an indication of what sorts of corrections we're actually considering, what's encoded in this equation. And because we've been talking about, it's been primarily diagrammatic now, it's helpful to see what this actually looks like as an equation. And from here, we can see that it's an 8-dimensional integral equation, which, at least to the best of my knowledge, has no readily accessible analytic solutions. So yeah, you can see in what way I mean that this is a self-consistent equation by the fact that this dress propagator appears with some complicated dependence inside these integrals. So because of this complexity, this motivates us to make, some kind of approximation. And in particular, we want to consider what kinds of approximations can we make while still retaining the interesting physics and still retaining the non-perturbative nature of quantum tunneling. And one such approximation is to insert the relativistic quantum mechanics propagator into the right-hand side of the equation. So essentially approximate the dress line with the results that we found in part 1. And when we do this, we find that we get a new one-loop equation, which looks like this, and still encodes QFT corrections. But crucially, this is a much, much simpler sort of structure because we don't have any dependence on G1 loop on the right-hand side. So now, in principle, if one were to find the relativistic quantum mechanics propagator, you could insert it and compute these integrals, and we would have the one-loop contribution. This is obviously harder in practice, but this is still a much simpler theory than the self-consistent equation. Now, it turns out this approximation is effectively a perturbative coupling approximation, where we're assuming that the original field couples to the new quantized field in a perturbative manner, but couples to the external field in to all orders. And this is analogous to the Fourier expansion in strong field QED. So in this case, you have an electron propagating in some strong external field, and they treat the interaction with the quantized photon field in a perturbative way. So it's completely analogous. And just to reiterate, this is now a one-loop approximation, which is no longer self-consistent. And I believe this is probably the simplest approximation which can capture these beyond relativistic quantum mechanics effects while still being compatible with tunneling. And also to emphasize that GRQM can in principle be determined numerically. And therefore, if we know this, we can also determine the one loop propagated numerically as well, simply via inserting it into the equation I just showed and modeling that numerically. Obviously, again, this is quite difficult, but still much simpler than solving an integral equation. So this just brings me to the quick summary of what we've just spoken about. So the key takeaway is that tunneling is a non-perturbative effect, but QFT is mostly done perturbatively. So we need to find a way to reconcile these two problems. And so what we consider in this talk is the tunneling of a neutral scalar field through a localized potential. And the way we obtain the tunneling regime is via an analytic continuation of S matrix elements, or these Feynman diagrams. And we find that when doing this, we can reproduce the transmission and reflection coefficients in accordance with relativistic quantum mechanics for some simple potentials. So now that with that formalism, what we can do is we can introduce, an extra term, now Lagrangian, which will couple via some cubic interaction. And then what we've done to describe this interaction, we've used a Hartree-Fock type approximation to sum a restricted class of Feynman diagrams, which is all orders in the interaction with our new field and with the external potential, which is, as I said before, crucial to make sure we retain tunneling. And then to simplify the physics, and because this is quite a complicated equation, we've applied a perturbative coupling approximation to find the one loop propagator. So really, what I want to emphasize is that we haven't been able to quantitatively answer the question, how do loop corrections impact tunneling? Do they increase the tunneling probability or not? But we have provided equations which provide a starting point to numerically model these effects and these corrections. Which brings me to some promising future directions. So as I said before, we need numerical modeling to characterize how these contributions affect transmission and reflection amplitudes. And the reason why this is a little bit difficult is because it'll likely involve, and this is something I've swept under the carpet a little bit in this talk, but for these particular Feynman diagrams, because we have an interaction with a non-Lorentz invariant external potential, it means that our Feynman diagrams don't have manifest Lorentz invariance. So we don't have, we can't employ some of the techniques that one would normally be able to employ to compute like higher order loop corrections. And that does increase the difficulty here. So it means you probably have to employ things like numerical contra integration or numerical loop integrals. But again, these rely on being able to locate the poles in your integral very well, which for these particular equations can be difficult depending on the choice of the potential. And in fact, most potentials make this a little bit difficult. And just going back to what originally motivated this problem is that we want to extend this to physically relevant Lagrangians of potentials, things like light matter interactions, fermions, or phenomenological nuclear potentials. So we know that in the context of something like false vacuum decay, when we add loop corrections, the effect is actually different, whether the loop correction is a fermion or a scalar. So it's natural to wonder whether this will also be the case for the quantum tunneling that I'm considering here. And I think one of the more interesting future directions, I think, which could be explored is a connection with the two-particle irreducible effective action. And this is effectively a way to also perform a non-perturbative resummation of a class of Feynman diagrams. And I would think it'd be interesting to see whether this formalism, gives equivalent results or is more effective. At the time of doing this research, I wasn't aware of this, so that's why I didn't pursue it, but I think could be promising. And then I think, again, going back to the fact that we eventually want to describe things like nuclear fusion, we'll need to find a way to extend these results to bound state tunneling problems. And this is one way might be with the beta-salpeter equation. So this, so we know bound states arise when we have poles in the S matrix. And this particular equation is a way to describe some bound states and via infinite order interactions. Again, not something I'm very familiar with, but I think might be a worthwhile avenue to pursue. So at this point, I think it's also worthwhile including a slightly more detailed discussion of what I've just spoken about. So in the first part, I just want to make another remark about the Klein paradox, and that our process of Feynman diagram summation relies on analytic continuation, which is actually not valid in the Klein regime. But in the context of this work, this is actually not a problem, and that's because no such regime exists, because there are no antiparticles in this system. So if there were antiparticles, you'd have to find another way to sum such a series. And this is also true of complex scalar fields coupling to ungauge potentials, where we have both any situation where both antiparticles and particles interact the same way with the potential, we will not see the Klein regime or the Klein paradox. There's also another subtle point I would like to make, and that's about the properties of delta functions. So I've said that we can think about a delta function as a limit of a rectangular barrier, but it's, not a silly question to ask. When does this actually correctly limit? And it turns out for scalar fields, the limiting behavior is correct, but for fermion fields, it's a little bit more difficult. So because the spinor field is discontinuous at the boundary, we find that the limit of a rectangular barrier cannot be naively taken to be a delta function. And this was something which was actually discovered in the 70s and the 80s. But so I think the upshot is that if we were to use the Feynman diagram method for spinor fields, which we have done, but I haven't shown here, but naively insert a delta function, we would find we get erroneous results. So in this particular context, you actually have to define a delta function as a limit of a rectangular barrier. So I highlight this just to say that there are some subtle properties, the subtle limits you need to be careful of. And then in part 2, some of you might have noticed that we've introduced a cubic interaction. So we find that when the external potential is 0, this theory reduces to the cubic Wick-Kukowski model. Now, this model has sometimes been used as a simplified model for spinless nucleon-meson interactions, but it's famously unstable, so it doesn't have a ground state. And this vacuum instability is, in fact, a non-perturbative effect. And it arises for any cubic scalar theory, and these theories are, for instance, super renormalizable. And this was shown, I think, in the 1960s. So it might be, it's a valid question to ask whether this presents some problems for this work. But it turns out that because we've truncated the phi space of using the Hartree-Fock approximation, we're effectively in something called the quenched regime. So this is where we don't get phi loops in our series of Feynman diagrams generated. And that's because this is a particularly good approximation. So it's called quenched when we have, let's say, a very heavy intermediate particle. But it's been shown that in this regime, there actually exists a range of mu coupling values which produce a stable ground state. So therefore, in this context, we have a stable theory, and this cubic instability shouldn't present any problems. Okay, so that more or less concludes my talk. Thank you all for listening, and I welcome any questions.
Thank you, Rosemary, for this nice talk. Beautiful slides. So we have some questions from the audience. You can go ahead. So there's so Ollie, maybe you go first.
Hi, thank you very much for a really nice talk. That was very clear. I did have a couple of questions. One, so you had this, you said something like a Fourier expansion. So you're resumming the classical field and you're doing a loop expansion for the quantum coupled field. There are some cases where you can do so analytically and work out what this Green's function is analytically. For example, in a constant field or in a plane wave field, or I believe in this Sauter potential 1 over Koch squared. I wonder, then you might be able to proceed analytically. And maybe that helps. I just wondering if that's something you've thought of.
Yeah, no, it is something I've thought of. I think the problem with things like plane wave fields is that you don't have a well-defined local potential or local tunneling problem.
Yeah, sorry, the first two were not strictly relevant for tunneling, I guess. How about I guess the third one, the Sauter potential, which is like 1 over Koch squared. So it's like you happen to be able to solve analytically.
Okay, thank you. No, that's definitely worth looking into.
In the field of strong field QED, it's like the go-to potential because you can solve it analytically. But yeah, thanks.
No worries.
maybe I can ask something. So you mentioned that there is an issue with you when you want to include fermions and it doesn't really work out. But
Yes. Do you mean in the like
in the last,
here?
yep.
Yep.
So is there a way to rectify the situation and you know, change the boundary condition to include fermions?
Yes, yes. There is a way to rectify. I mean, this is solved in the context of like in the context of the Dirac equation. You just have to be careful with specifying your jump conditions. But in the context of our work, what it means is that if you want to treat the tunneling of a fermion, you can't just insert a delta function into our integral equation. You actually have to insert the Fourier transform of the rectangular barrier and then take the limit.
Okay.
Yeah, is what I'm trying to say. But that turns out to be quite difficult. Yeah, but that's how you have to do it. Does that answer your question?
Yeah, no, I think I got it. So in your formalism, your initial state is a single particle that tunnels to the barrier.
Yes.
Can you extend it to multi-particle, like towards going to the bound state? I mean,
I mean, in principle, one could. It's not something that I spoke a little bit about this by using the beta salpeter equation, but I think the problem is that we still haven't found analytic solutions for single particle, like QFT corrections in the context of single particles. So I don't know if the best approach is then to start looking at like a bound state problem, even though that is where you want to be in the end.
yeah, got it.
Yeah.
Thanks. Thank you.
No. Also, to the best of my knowledge, I don't know if QFT has dealt with very large bound state problems very well. Yeah, I think we've only got like the hydrogen atom, maybe a few like small proton systems or something, but even then, or proton neutron, should I say?
Yeah. Great. So no more questions from the audience. Then let's thank Rosemary again. And I'll remind you that the next talk in the series is going to be by Simone Blasi on October 17th, right? Okay, good. So yeah, thanks again, Rosemary, and see you all next month.
Thank you all for having me. Goodbye.
Yep.
Thank you, Rosemary. Thanks a lot.